For problem number 9, this one is a line of charge. It says it has a positive charge Q, uniformly distributed, and the left end is where we want to identify the electric field. So since it's a positive charge, we know that all these positive charges are going to push or create an electric field going out of the positive, and at this point, it would point to the left. Now, when we think about this problem, we need to take pieces of charge, and if I take this dq here over the d length, we can use the whole idea that there's uniform distribution to solve this problem. So, and then we're going to start from this position all the way out to the last dq and add them all together. So the first step always is to write out your fundamental principle. And we want to think about what our radius is. So the radius is the distance, and we can see here that it starts off at r. And then as we take pieces of charge all the way along to the very outer position of the rod, we know that we're going to have a last position right here at r plus L, because the length of the rod is L and it doesn't start till position R. So at that point, I know those are my limits, R to R plus L. The thing that we want to think about next is what variable is changing. Well, we know that dq is increasing as we add all the dq's together, but that piece of dq stays pretty constant. What we also know is that the distance, as we take pieces of length, the length is also, the pieces of length as we add it together is also changing. So I want you to find the relationship between charge and length using the fact that there's uniform distribution. So lambda is equal to the full charge over the full length, which is also equal to one piece of charge, so dq represents one piece over one piece of length dl. Now, when we are working in this scenario, pieces of length can correspond to the distance that the piece of charged object is from the position we're looking in question. And so in this scenario, I can take my r squared and represent that as my dl. And it doesn't really matter how you do this. One thing I like to do is that if I see it's on an x-axis, I will generally use this length to represent the variable of that axis. So instead of dl, I'll call it dx. Instead of dl here, I'll call that dx. And then because r is my initial distance, I represented that here, and I can call the changing distance x squared. So let's move on. We have a variable x and a variable q, and we want to make sure that we're integrating with respect to one changing variable. So since theta is a constant, I can represent dq as, lambda, lambda dx. And so now I'm going to go in and substitute the integral from r to r plus L. My dq is lambda dx over x squared, and the lambda is a constant, so I can write it out as k lambda, the integral of dx over x squared. But when I'm working with variables in the denominator, I find it a lot easier to integrate when I put it in the numerator with a negative power. So I'm going to use my property of integration with polynomials, and I'm going to add, I can get rid of my integral, add to the power to make it -1, and divide by that new power, and then I take my limits from r plus L or r to r plus l, and then I plug in those values. So in the end, I get negative k lambda, 1 over x, and then I'm going from the limits of r plus l to r, and then I am going to plug in negative k lambda from my final limit, r plus l, minus my initial limit r, and I forgot to put the negative here. And even though this is a good final answer, because I have a negative in the front, I can clean it up by rewriting it as k lambda, distribute the negative to both sides, and now I have 1 over r in front minus 1 over r plus l after it. And that is your answer for 7.